Greetings, curious minds, and welcome back to Vibing Science. Tonight, as the world quiets around us, we embark on a journey into the very fabric of light itself, to a place where even the faintest whisper of a photon holds profound secrets. Imagine, if you will, the monumental challenge of capturing a single, solitary particle of light, the fundamental carrier of information from the cosmos, or the deepest quantum realms. For millennia, our senses and tools have striven to pierce the veil of the unseen. But today, we possess instruments capable of detecting just one of these elusive messengers. We're talking about the Superconducting Nanowire Single-Photon Detector, the SNSPD. This is a marvel of modern physics, and it's not just observing the universe. It's fundamentally reshaping our understanding of it. Settle in, find your focus, and prepare to have your mind expanded. If you enjoy this exploration, please consider leaving a like, a share, or a comment. It truly helps us continue these deep dives. Now, let the journey begin. Welcome back, my friends, to the quiet hum of discovery. Tonight, we journey into a realm so exquisitely precise, so incredibly sensitive, that it touches the very fabric of existence itself, the world of the invisible catchers. We're talking about light, not just light as we commonly perceive it, but the most fundamental particle of light, the single photon, and the remarkable technology designed to not just see, but truly feel these fleeting quanta, the single photon detector. Imagine trying to catch a single raindrop in a vast ocean, or hear the whisper of a single atom amidst a roaring storm. That's the kind of challenge we face when we try to detect a solitary photon. Light, as you know, is made up of these tiny packets of energy, photons. In our everyday lives, we're bathed in billions upon billions of them, arriving in a continuous deluge, painting the world in all its vibrant hues. Our eyes, marvels of biological engineering, are adept at capturing these massive quantities of photons, converting them into the electrical signals our brains interpret as sight. But what if you need to detect just one? What if that single photon carries a crucial piece of information, a quantum secret, or the faint echo of a distant, hidden world? Our everyday detectors, even the most sensitive camera sensors, simply aren't up to the task. They're designed for floods, not individual drops. This is where the truly extraordinary science of single-photon detection steps onto the stage. It's a field born out of necessity, driven by the insatiable curiosity of scientists pushing the boundaries of what's possible, peering into the universe at its most granular level. For decades, scientists have been developing various methods to achieve this seemingly impossible feat. Think of them as quantum sentinels, standing guard, waiting for that singular, ethereal knock. Early attempts involve highly specialized photodetectors, often requiring extreme cooling or complex amplification schemes. They worked to a degree, but often came with trade-offs. Perhaps they weren't efficient enough, meaning many photons slipped through undetected, or they were prone to dark counts, mistaking random noise for an actual photon. And sometimes, they just weren't fast enough to catch those fleeting moments of light. But then, as so often happens in the relentless march of scientific progress, a truly revolutionary leap occurred. A concept emerged from the depths of quantum mechanics and material science that promised to overcome these limitations. It centered around a phenomenon so profound, it still holds tantalizing mysteries for physicists: superconductivity. In the year 2001, at the venerable halls of Moscow State Pedagogical University and the University of Rochester, the first whispers of a new kind of single-photon detector began to materialize. It was based on a simple yet elegant idea: a current-biased superconducting nanowire. Imagine a wire so impossibly thin, so exquisitely crafted, that it could react to the impact of a single photon. This was the genesis of what we now know as the Superconducting Nanowire Single-Photon Detector, or SNSPD. It took a few more years, a patient, painstaking effort by brilliant minds, before the first fully operational prototype was demonstrated in 2005. This pivotal moment was brought about by the collaborative genius of the National Institute of Standards and Technology in Boulder, Colorado, and BBN Technologies as part of the ambitious DARPA quantum network. They were building the very infrastructure for a quantum future, and they needed detectors that could reliably and efficiently catch individual photons, the very carriers of quantum information. And what they created, what they demonstrated, was nothing short of astonishing. Fast forward to today, to the year 2023, and the SNSPD stands as the undisputed champion, the fastest single-photon detector for photon counting known to science. Let that sink in for a moment. In a world where every nanosecond can carry crucial data, where every fleeting event matters, the SNSPD reigns supreme. This isn't just a niche laboratory curiosity. The SNSPD is a foundational, enabling technology for the burgeoning fields of quantum optics and optical quantum technologies. These are the fields that promise to revolutionize everything from computing and communication to medicine and fundamental physics. Imagine quantum computers that can perform calculations currently unfathomable, or secure communication networks impervious to eavesdropping. The SNSPD is a vital component in making these dreams a reality. The reason for its supremacy lies in a trio of truly remarkable characteristics. SNSPDs boast incredibly high detection efficiency. This means that when a photon actually hits the detector, there's an extremely high probability it will actually be counted. Other detectors often miss a significant percentage of incoming photons, like a net with large holes. The SNSPD, by contrast, is a finely woven, almost perfect trap. Secondly, they have an astonishingly low dark count rate. Remember those phantom signals, those false positives that can plague less sophisticated detectors? SNSPDs minimize these to an almost unimaginable degree. It's like having a security system that almost never cries wolf. This is crucial when you're searching for incredibly faint signals, where a single false alarm could obscure a genuine discovery. And thirdly, they possess incredibly low timing jitter. This might sound like a technical detail, but it's profoundly important. Timing jitter refers to the uncertainty in precisely when a photon is detected. Imagine trying to measure the exact moment a light switch is flicked on, but your stopwatch has a slight, unpredictable delay. Low timing jitter means the SNSPD can tell you, with exquisite precision, the exact moment that photon arrived. This is invaluable for applications where timing is everything, like creating ultra-secure quantum encryption or mapping events at an atomic scale. Such an advanced technology, as you might expect, comes with a price tag. As of 2023, commercial SNSPD devices, often integrated into sophisticated multi-channel systems, can range in price, typically starting around 100,000 euros. This reflects the cutting-edge research, the intricate fabrication processes, and the demanding cryogenic environments required for their operation. But for the applications they enable, for the mysteries they help unravel, this investment is proving invaluable. Now, one of the challenges with these ultra-thin, ultra-precise devices has been their manufacturing. Traditionally, creating these impossibly narrow nanowires required electron lithography, a highly specialized and expensive process. But recent breakthroughs have hinted at a fascinating possibility. What if we could make these superconducting wires wider, wide enough that we could use more conventional, and therefore cheaper, optical lithography? And indeed, it was recently discovered that superconducting wires as wide as 1.5 micrometers could still detect single infrared photons. To put 1.5 micrometers into perspective, it's roughly the size of a tiny bacterium. Still incredibly small, but significantly larger than the initial nanowires. This is a game-changer for applications that require large photodetector areas, where the cost of electron lithography would be prohibitive. One particularly exciting application for these larger area SNSPDs lies in the profound quest for dark matter. The universe, we believe, is largely composed of this mysterious, invisible substance that interacts with normal matter only through gravity. Scientists are building elaborate experiments, often deep underground, to try and detect these elusive particles. One promising approach involves using scintillating crystals, materials that emit faint flashes of light when an energetic particle passes through them. Imagine a large crystal, perhaps made of gallium arsenide, suitably doped with silicon and boron. This crystal, when cooled to cryogenic temperatures, becomes a luminous scintillator, producing tiny bursts of light when a dark matter particle, in theory, interacts with it. Crucially, it has no apparent afterglow, meaning the light quickly fades, allowing for precise timing. And these crystals are now commercially available in large, high-quality forms. To detect the incredibly faint flashes from these crystals, to truly see the interaction of a dark matter particle, you need a detector of unparalleled sensitivity. You need an SNSPD. So, how does this incredible device actually work? What is the fundamental principle behind its ability to catch these ghostly individual photons? At its heart, an SNSPD consists of a thin, typically around 5 nanometers, and narrow, around 100 nanometers, superconducting nanowire. To give you a sense of scale, a human hair is about 80,000 to 100,000 nanometers wide. So, these nanowires are hundreds of thousands of times thinner than a human hair. The total length of this nanowire is often hundreds of micrometers, but it's patterned into a compact, meandering geometry, like a tiny, intricate maze. This allows it to cover a larger square or circular pixel area, maximizing its chances of catching a photon, while still maintaining its delicate properties. Now, for this nanowire to exhibit its magical superconducting properties, it needs to be cooled to extremely low temperatures, well below its superconducting critical temperature. We're talking about temperatures just a few degrees above absolute zero, the coldest possible temperature in the universe. This is typically achieved using specialized cryocoolers, often involving liquid helium, which can bring the temperature down to the range of 1 to 4 Kelvin. Once it's sufficiently cold, the nanowire is biased with a direct current, meaning a steady flow of electricity is passed through it. This current is carefully set to be very close to, but slightly less than, the superconducting critical current of the nanowire. The critical current is the maximum current a superconductor can carry before it loses its superconductivity. Think of it like a dam holding back water. The bias current is just shy of the dam's breaking point. Here's where the magic truly happens. When a photon, a single packet of light, strikes this delicate nanowire, it carries energy. Even though it's incredibly tiny, that energy is enough to disrupt the delicate balance within the superconductor. In a superconductor, electrons pair up into what are called Cooper pairs, and these pairs can move through the material without any resistance. But the incoming photon, with its kinetic energy, breaks these Cooper pairs apart. This breaking of Cooper pairs creates a localized hotspot within the nanowire. Imagine a tiny, almost imperceptible disturbance, a microscopic ripple in the perfect, unimpeded flow of electricity. This hotspot is a region where the material temporarily loses its superconductivity and becomes resistive, meaning it now offers resistance to the flow of current. Because this localized region now has electrical resistance, it effectively reduces the local critical current of the nanowire to below that of the bias current. Suddenly, that dam we talked about can no longer hold back the current. Most of the bias current, which was flowing effortlessly through the superconductor, is now forced to shunt or divert to a readout amplifier. This sudden diversion of current creates a measurable voltage pulse. It's like a sudden spike in an electrical signal, a clear blip that tells us a photon has been detected. This voltage pulse is typically quite strong, usually around the bias current multiplied by the 50 ohm input impedance of the readout amplifier, making it easy to register. But the process doesn't end there. With most of the bias current now flowing through the amplifier, the hotspot in the nanowire The region that briefly lost its superconductivity cools down almost instantaneously, and as it cools, it quickly returns to its superconducting state, ready to detect another photon. This self-resetting mechanism is crucial for the SNSPD's remarkable speed. The time it takes for the current to return to the nanowire is usually determined by the inductive time constant of the nanowire itself, which is its kinetic inductance divided by the impedance of the readout circuit. For the device to reset properly, this inductive time constant needs to be slightly slower than the intrinsic cooling time of that tiny hotspot. While the SNSPD is an unparalleled photon counter, it's worth noting that it doesn't quite match the intrinsic energy or photon number resolution of another type of superconducting detector, the transition edge sensor. Transition edge sensors can, in some cases, determine the exact energy of an incoming photon or even count how many photons arrive simultaneously. However, SNSPDs are significantly faster and can operate at higher temperatures, making them more practical for many real-world applications. Intriguingly, researchers are finding ways to achieve a degree of photon number resolution even with SNSPDs by arranging them in arrays or using advanced readout techniques, effectively allowing a team of SNSPDs to discern more complex photon arrival patterns. Most SNSPDs are crafted from a fascinating material called niobium nitride, or NBN. Niobium nitride is chosen because it has a relatively high superconducting critical temperature, around 10 Kelvin. This means it can maintain its superconducting properties at temperatures compatible with readily available liquid helium or modern closed-cycle cryocoolers, which typically operate in the 1 to 4 Kelvin range. The intrinsic thermal time constants of NBN are also incredibly short, meaning that hotspot cools down in less than 100 picoseconds, contributing to the SNSPD's astonishing speed. To further boost the absorption of photons, SNSPDs are often integrated with clever optical designs. Imagine adding an optical cavity, like a tiny mirror, to trap the light and give it more chances to interact with the nanowire. Or integrating them into a photonic waveguide, a tiny channel that guides light directly to the detector. Even adding nanoantenna structures, microscopic antennas designed to capture and focus light onto the nanowire, can dramatically increase their efficiency. These sophisticated engineering techniques have led to SNSPD cavity devices made from materials like NBN, NBTN, WC, and MOSI, demonstrating fiber-coupled device detection efficiencies greater than 98% at specific wavelengths, like 1550 nanometers, with count rates reaching into the tens of megahertz. It's important to understand that the detection efficiency of these devices is often optimized for a specific range of wavelengths. A detector designed to catch infrared light might not be as efficient at catching visible light, and vice versa. This optimization is crucial for tailoring SNSPDs to their particular applications. Beyond detection efficiency, SNSPDs have demonstrated exceptionally low jitter, as we discussed earlier. We're talking about an uncertainty in photon arrival time as low as 3 picoseconds at visible wavelengths. To put that into perspective, a picosecond is 1/trillionth of a second. This level of precision is almost mind-boggling, and it's been verified for photon energies down to 3.5 micrometers wavelength. This exquisite timing resolution makes SNSPDs invaluable for applications like time-correlated single-photon counting, where precisely measuring the time difference between photon arrivals can reveal deep insights into molecular dynamics or quantum phenomena. And then there's the incredibly low rate of dark counts. These are those pesky false alarms, voltage pulses that occur even when no photon has been detected. SNSPDs exhibit remarkably few of these, further cementing their reliability. Additionally, the dead time, the brief period after a detection event during which the detector is insensitive, is astonishingly short, on the order of a few nanoseconds. This short dead time translates into very high saturation count rates, meaning the detector can handle a barrage of photons without getting overwhelmed. It also enables specialized measurements like anti-bunching, where a single detector can confirm the emission of single photons, a crucial test in quantum light sources. While SNSPDs excel at detecting visible and near-infrared light, detecting longer wavelength photons, such as those in the mid-infrared range, has historically been more challenging, with detection efficiency decreasing significantly. But scientific progress is relentless. Recent efforts have focused on exploring even narrower nanowires, down to 20 or 30 nanometers wide, made from NBN, as well as investigating alternative superconducting materials. Materials with even lower superconducting critical temperatures, like tungsten silicide, niobium silicide, molybdenum silicide, and tantalum nitride, are being rigorously studied. These materials allow the devices to operate at even colder temperatures, which can enhance their sensitivity to lower energy, longer wavelength photons. Indeed, single photon sensitivity up to 10 micrometers wavelength has recently been demonstrated in a tungsten silicide SNSPD. This opens up entirely new frontiers for mid-infrared imaging and spectroscopy. Furthermore, alternative thin film deposition techniques, such as atomic layer deposition, are being explored to extend the spectral range and enhance the scalability of SNSPDs to larger areas, making them more practical for widespread use. Even high-temperature superconductors, which can operate at slightly warmer cryogenic temperatures, are being investigated for SNSPD applications, with some encouraging recent reports. Magnesium diboride, for instance, has shown some single-photon sensitivity in the visible and near-infrared range, pushing the boundaries of what's possible. And the future holds even more promise. There is considerable interest and effort being poured into scaling up SNSPDs to create large, multi-pixel arrays and even full cameras. Imagine an array of thousands or even millions of these individual photon catchers working in concert. A kilopixel SNSPD array has already been reported a monumental achievement. One of the key challenges in building such large arrays is managing the readout. How do you extract the signals from so many individual detectors simultaneously? Researchers are tackling this with ingenious solutions like multiplexing, where multiple detectors share readout lines, or even using digital readout systems based on superconducting single-flux quantum logic, an entirely new paradigm in ultra-fast, low-power electronics. So, from the fundamental principles of superconductivity to the cutting edge of materials science and quantum engineering, the superconducting nanowire single-photon detector is a testament to human ingenuity. It's a device that allows us to not just glimpse, but truly interact with the most fundamental particles of light, opening doors to a future filled with quantum possibilities and deeper understandings of the cosmos around us. As we continue to delve into the applications of this remarkable technology, you'll see just how profound its impact promises to be. So, how exactly do these marvels work? How does a wispy, barely there thread of superconducting material manage to catch the most elusive particle in the universe, the single photon? It all comes down to a delicate dance between quantum mechanics and precise engineering. Imagine a microscopic tightrope walker, a nanowire so incredibly thin it's just about 5 nanometers thick and only 100 nanometers wide. To put that into perspective, if a human hair were a massive suspension bridge, this nanowire would be a single strand of silk, almost invisible to the naked eye. This nanowire isn't just a straight line. It's intricately patterned into a compact meander, creating a small square or circular pixel. This clever design maximizes the surface area to ensure a higher chance of catching a photon. Now, this tiny tightrope walker needs special conditions. It's cooled to temperatures well below its superconducting critical point. Think of it as an extremely cold environment, where the electrons inside the nanowire behave in a very peculiar way. They pair up into what are called Cooper pairs, and these pairs can flow through the material with absolutely no resistance. This is the essence of superconductivity. While in this supercooled state, The nanowire is also biased with a direct current, a flow of electricity that's almost, but not quite, at its maximum capacity. It's like having a river flowing just below the brim, ready to overflow at the slightest disturbance. This is where the photon enters the stage. When a single photon, that tiny packet of light energy, strikes the nanowire, it disrupts this delicate balance. The photon carries just enough energy to break apart some of those Cooper pairs. This breakage is critical because it locally reduces the nanowire's ability to carry current. The critical current, the maximum current it can carry while remaining superconducting, momentarily dips below the bias current that's already flowing through it. What happens next is a miniature yet profound event. The disrupted area, now devoid of enough Cooper pairs, momentarily loses its superconductivity. It becomes a localized hotspot, a tiny region with finite electrical resistance. Because this resistance is significantly higher than the impedance of the attached readout amplifier, the bias current, which was flowing through the superconducting nanowire, suddenly finds an easier path. It gets shunted away from the nanowire and into the amplifier. This sudden diversion of current creates a measurable voltage pulse. It's like a tiny electrical hiccup, a signal that tells us a photon has been detected. This voltage pulse is precisely what we are looking for. But the story doesn't end there. As the bias current rushes into the amplifier, the localized hotspot on the nanowire begins to cool down. Without the constant flow of current pushing through it, the disrupted Cooper pairs have a chance to reform, and the region rapidly returns to its superconducting state. This self-resetting mechanism is crucial for the device's ability to detect subsequent photons. The time it takes for the current to return to the nanowire is determined by the nanowire's kinetic inductance and the impedance of the readout circuit. It's a precisely calibrated system, ensuring the detector is ready for the next incoming photon almost instantaneously. While SNSPDs might not inherently offer the same energy or photon number resolution as some other superconducting detectors, their sheer speed and ability to operate at relatively higher temperatures, typically between 1 and 4 Kelvin, make them invaluable. This temperature range is compatible with readily available liquid helium or modern closed-cycle cryocoolers, making their implementation more practical. The intrinsic thermal time constants of the materials used in SNSPDs, particularly niobium nitride, are incredibly short, leading to astonishingly fast cooling times after photon absorption, often less than 100 picoseconds. This allows for extremely high count rates, meaning these detectors can register a vast number of photons in a very short period. To further enhance their efficiency, SNSPDs are often integrated with optical cavities, photonic waveguides, or even nanoantenna structures. These clever additions effectively catch and direct more incoming photons towards the active region of a nanowire. With these enhancements, some SNSPDs have achieved detection efficiencies greater than 98% at specific wavelengths, coupled directly to optical fibers, with count rates in the tens of megahertz. Beyond efficiency, SNSPDs boast incredibly low timing jitter, a measure of the uncertainty in the photon's arrival time. Some devices have demonstrated jitter as low as 3 picoseconds at visible wavelengths. This precision is absolutely critical for applications like time-correlated single-photon counting, where knowing the exact arrival time of a photon is paramount. Furthermore, these detectors exhibit exceptionally low dark count rates, meaning they rarely register a detection event when no photon is actually present. In their dead time, the brief interval after a detection event during which the detector is insensitive is on the order of mere nanoseconds. This short dead time allows for very high saturation count rates, enabling advanced quantum measurements with a single detector, even when photons arrive in rapid succession. However, the detection efficiency of standard SNSPDs does tend to decrease significantly for longer wavelength photons. To overcome this, researchers are exploring narrower nanowires and alternative superconducting materials with even lower critical temperatures, such as tungsten silicide and molybdenum silicide. These advancements have pushed the boundaries of single-photon sensitivity, with some SNSPDs now able to detect photons with wavelengths up to 10 micrometers. The future of SNSPDs also lies in scalability. There's immense interest in creating large multi-pixel arrays and even full kilopixel cameras. The challenge here is the readout mechanism, but innovative solutions like multiplexing and digital readout using superconducting single-flux quantum logic are paving the way for these advanced imaging systems. In essence, the superconducting nanowire single-photon detector is a marvel of quantum engineering, a tiny quantum trap that capitalizes on the delicate balance of superconductivity to reveal the invisible dance of individual photons. It's a technology that's not just observing the quantum world, it's actively participating in its unfolding. We ventured deep into the subtle quantum realm, exploring the intricate mechanics of how these superconducting nanowire single-photon detectors, or SNSPDs, actually work. We've unraveled the delicate balance of current and temperature, the fleeting disruption of Cooper pairs, and the precise, almost balletic, formation of a hotspot that signals the arrival of a single, elusive photon. Now, as the ambient hum of our understanding settles, it's time to gaze outwards to truly comprehend the profound impact these remarkable devices are having and will continue to have on our world. For the SNSPD is not merely a scientific curiosity. It is a key, unlocking doors to realms of knowledge and technology previously unimaginable. Think of it, the fastest single-photon detector known to science. This isn't just about speed for speed's sake. It's about capturing moments in time so infinitesimally small, so fleeting, that they would be lost to any other instrument. This incredible swiftness, coupled with their astonishing sensitivity and remarkably low noise, positions SNSPDs as foundational technologies in a burgeoning era of quantum innovation. Their initial forays have been, perhaps predictably, into the hallowed halls of quantum information. Imagine a world where secrets are transmitted with unbreakable security, guaranteed by the very laws of physics. That's quantum key distribution, and SNSPDs are vital components in its realization, ensuring that any attempt to eavesdrop on these quantum communications would inevitably alter the photons being exchanged, instantly revealing the intrusion. And then there's optical quantum computing. While still in its nascent stages, the promise of quantum computers to solve problems that are currently intractable for even the most powerful classical supercomputers is breathtaking. SNSPDs act as the precise eyes of these experimental quantum processors, detecting the quantum states of photons as they are manipulated, allowing scientists to verify and advance these complex calculations. They are the essential link, translating the ethereal quantum world into measurable data that we can understand and build upon. But the reach of these detectors extends far beyond the confines of quantum labs. Consider the world of advanced diagnostics. In the intricate tapestry of modern microcircuitry, where transistors are measured in nanometers, even the slightest defect can lead to catastrophic failure. SNSPDs are being deployed to image infrared photoemission, essentially peering into the microscopic architecture of CMOS circuits, identifying these minuscule flaws with unprecedented precision. This capability is revolutionizing quality control and pushing the boundaries of what's possible in semiconductor manufacturing. Or turn your gaze skyward to the vast expanse of the cosmos. Deep space optical communication is an ambitious endeavor, aiming to transmit colossal amounts of data across staggering distances. Imagine a future where probes on distant planets or spacecraft exploring the outer reaches of our solar system can beam back high-definition imagery and scientific data at incredible rates. SNSPDs, with their exquisite sensitivity to even the faintest whispers of light, are crucial for receiving these ultra-weak signals from millions, even billions of miles away. They are the ears that pick up the faintest cosmic whispers, translating them into narratives of discovery. Closer to home, these detectors are transforming our understanding of the fundamental world around us. In the realm of dark matter searches, scientists are attempting to detect the elusive particles that make up the vast majority of matter in our universe, yet interact with almost nothing. Experiments utilizing scintillating crystals like gallium arsenide, doped with silicon and boron, produce faint flashes of light when a dark matter particle, however rarely, interacts with an atom within the crystal. These incredibly faint, fleeting signals are precisely what SNSPDs are designed to catch, offering a new avenue in humanity's quest to unveil one of the universe's greatest mysteries. The ability to detect single infrared photons, even in wider superconducting wires, signifies a breakthrough here, allowing for larger detection areas and potentially more economical construction, making these monumental searches more feasible. And what about the search for other worlds? The detection of exoplanets, those distant celestial bodies orbiting other stars, is an endeavor that constantly pushes the limits of our observational capabilities. While direct imaging of exoplanets remains incredibly challenging due to the overwhelming glare of their parent stars, SNSPDs are playing an increasingly important role in advanced techniques that aim to separate the faint light reflected from an exoplanet from its brilliant star. They are helping us to perceive the subtle shimmering of distant worlds, guiding our understanding of planetary formation and the potential for life beyond Earth. The versatility of SNSPDs is truly remarkable. From the microscopic precision of on-chip quantum optics, where light is guided and manipulated on integrated circuits, to the biological insights gained from detecting singlet oxygen luminescence, a key indicator in various biological and chemical processes, these detectors are making their mark. They are crucial for LiDAR systems, enhancing their range and accuracy for everything from autonomous vehicles to atmospheric research. They assist in characterizing single-photon emitters, those tiny quantum light sources essential for many quantum technologies. They even aid in the detection of individual alpha and beta particles, offering new avenues in nuclear physics and radiation monitoring. The commercial landscape for SNSPDs is also rapidly expanding. What began as a niche academic pursuit is now a booming industry, with companies worldwide offering complete, sophisticated single-photon detection systems. While the price tags for multi-channel systems might seem substantial, often in the realm of hundreds of thousands of euros, this reflects the cutting-edge nature of the technology and its specialized applications. However, the discovery that wider superconducting wires can detect single infrared photons, allowing for optical lithography in their construction rather than more expensive electron lithography, hints at a future where these devices become more accessible for applications requiring larger detection areas, potentially driving costs down. The path forward for SNSPDs is brimming with innovation. The drive to scale these remarkable devices into large multi-pixel arrays, essentially creating high-resolution single-photon cameras, is a significant challenge, but one that researchers are actively addressing. Imagine a camera that can detect every single photon striking its sensor. The implications for everything from medical imaging to astronomical observation are profound. Overcoming the complexities of readout for such large arrays, perhaps through advanced multiplexing techniques or the lightning-fast logic of superconducting single-flux quantum circuits, will be a monumental step forward. Furthermore, the quest to extend the operational wavelength of SNSPDs continues. While they excel in the optical and near-infrared, pushing their sensitivity into the mid-infrared and beyond opens up entirely new frontiers, particularly in areas like chemical sensing and thermal imaging. Materials like tungsten silicide, niobium silicide, and molybdenum silicide, with their lower superconducting critical temperatures, are being meticulously investigated, demonstrating sensitivity at wavelengths up to an astonishing 10 micrometers. This expansion of their spectral range will unlock even more diverse applications, further cementing their role as indispensable tools in scientific discovery and technological advancement. Ultimately, the superconducting nanowire single-photon detector is a testament to human ingenuity, a bridge between the ethereal quantum world and the tangible realm of technological application. It is a device that allows us to perceive the faintest echoes of light, transforming those whispers into torrents of information that deepen our understanding of the universe, from its smallest particles to its most expansive frontiers. As we continue to refine their capabilities, to integrate them into ever more complex systems, SNSPDs will undoubtedly continue to illuminate new pathways, pushing the boundaries of what we thought was possible and bringing into focus the subtle, beautiful intricacies of our shared reality. The horizon, it seems, is always expanding when you have eyes that can see the unseen. And so, as our exploration draws to a close, we emerge from the fascinating world of superconducting nanowire single-photon detectors. From the ingenious physics of superconductivity to the groundbreaking applications across quantum computing, deep space communication, and even the hunt for dark matter, these devices stand as a testament to human ingenuity and our unyielding quest to understand the universe at its most fundamental level. They remind us that even the smallest units of light can reveal the grandest secrets. Thank you for joining me on this deep dive. I hope this narration offered you a moment of peace, focus, or perhaps sparked a new wonder. If you found value in this journey, please consider liking this video, sharing it with someone who might appreciate it, and subscribing or following for more explorations into the cosmos and beyond. What were your thoughts on tonight's journey? And what incredible scientific mysteries would you like us to unravel next? Until our next shared exploration, stay curious and keep vibing with science.